I'll start by briefly reviewing the topics covered in this week's lecture. So,
So,
in
in
this
this
week,
week,
topics
topics
covered were
covered
errors and convergence. For
for
all
all
numerical
numerical
methods,
methods,
they
they
are
are
not
not
found
found
out
out
exactly.
exactly.
So,
So,
there
there
will
will
be
be
error
error
to
to
the
the
actual
actual
solutions.
solutions.
So,
So,
how
how
we
we
know
know
calculate
calculate
the
the
error?
error?
Uh,
Uh,
there are
there are
different
different
ways
ways
to
to
calculate
calculate
error.
error,
And
and
before
before
that,
that,
there are
there are
different
different
sources
sources
which
which
errors
errors
comes
comes
from.
from.
First
First
thing,
thing,
any
any
in
in
FEM
FEM
we
we
approximate
approximate
the
the
uh, domain
domain
into
into
discretize the
discretize the
domain
domain
into
into
subdomains.
subdomains,
Especially
especially
in
in
2D
2D
and
and
3D
3D
geometry,
geometry.
the
The
square
square
root
root
geometries,
geometries,
everything
everything
will
will
be
be
approximated
approximated
into
into a
some
some
linear
linear
elements.
elements.
So
So
geometry
geometry
won't
won't
be
be
exactly
exactly
correct.
correct.
So
So
that
that
causes
causes
some
some
kind
kind
of
of
error
error
called
called
computational
computational
domain
domain
error.
error.
Then
Then
we
we
take
take
the
the
solution
solution
as
as
an
an
polynomial
polynomial
of
of
some
some
order.
order.
That
That
is
is
another
another
assumption,
assumption,
which
which
is
is
causes
causes
an
an
error
error
known
known
as
as
approximation
approximation
error.
error.
Computational
Computational
domain
domain
based
based
on
on
geometry.
geometry.
This
This
is
is
based
based
on
on
assumed
assumed
polynomial.
polynomial.
Then
Then
what
what
we
we
need
need
to
to
calculate
calculate
the
the
integrals,
integrals,
and
and
we
we
use
use
a
a
quadrature
quadrature
rule
rule
to
to
calculate
calculate
the
the
integral.
integral.
So
So
those
those
the
the
integrals
integrals
which
which
we
we
calculate,
calculate,
especially
especially
while
while
doing
doing
the
the
coding,
coding,
they're
they're
calculated
calculated
numerically,
numerically,
and
and
they
they
introduce
introduce
some
some
error.
error.
It
It
is
is
called
called
quadrature
quadrature
error.
error.
Then
Then
finally,
finally,
the
the
computers
computers
has
has
some
some
significant
significant
digits,
digits,
and
and
over
over
there
there
will
will
be
be
a
a
error
error
in the
in the
calculating
calculating
the
the
like
like
truncation
truncation
error,
error,
like
like
large
large
digits
digits
of
of
the
the
number
number
will
will
be
be
removed,
removed,
and
and
then
then
some.
some.
So
So
that
that
introduces
introduces
an
an
error
error
called
called
finite
finite
arithmetic
arithmetic
error,
error.
and
And
this
this
one
one
depends
depends
on
on
the
the
system
system
which you
which you
are
are
using
using
and
and
the
the
variable
variable
defining,
defining,
something
something
like
like
integer
integer
or
or
double
double
or
or
float.
float.
It
It
depends
depends
on
on
those
those
kinds
kinds
of
of
things.
things.
So
So
these
these
are
are
the
the
like
like
sources
sources
of
of
errors.
errors.
So
So
we
we
have
have
several
several
sources
sources
of
of
errors.
errors.
So
So
in
in
order
order
to
to
evaluate
evaluate
them,
them,
even
even
for
for
evaluating
evaluating
the
the
errors,
errors,
there are
there are
different
different
ways
ways
to
to
evaluate
evaluate
the
the
error.
error.
We'll
We'll
see
see
the
the
measures
measures
to
to
evaluate
evaluate
error.
error.
First
First
way
way
is
is
point-wise
point-wise
error.
error.
So
So
let's
let's
say
say
that
that
our
our
this
this
is
is
our
our
domain,
domain,
and
and
our
our
solution
solution
is
is
U,
U,
and
and
FEM
FEM
solution
solution
is
is U of
UH
UH
of
of
X.
X.
Then
Then
pointwise
pointwise
error
error
is
is
a
a
function
function
of
of
the
the
domain,
domain,
which is
which is
nothing
nothing
but the
but the
difference
difference
between
between
the
the
actual
actual
solution
solution
minus
minus
FEM
FEM
solution,
solution,
exact
exact
solution,
solution,
FEA
FEA
solution.
solution.
So
So
this
this
will
will
be
be
a
a
also
also
be a
be a
function
function
over
over
the
the
whole
whole
domain.
domain.
it's not a single value. Second one is maximum norm error. It is defined as U minus UH. This is the how we represent the maximum norm error. It is nothing but the difference between the exact solution and the FEM solution, same like the previous one, but just take the maximum value of this point and just say that is the maximum, that is defined as maximum norm error. Third one is energy norm error. It is represented in this manner. M is kind of an delta, 2m is kind of an order of the differential equation. It is defined in this manner. It's like derivatives of the original solution minus derivatives of the approximated solution, summation and then integrated, and then its power is taken to the half. It's like equivalent to the energy in physical problems, like mechanical problems. This term will be similar to the energy. Final one is L2 norm error. It is U minus UH. It is defined in this manner. A to B U minus UH square and its square. L2, it's kind of a, it's equivalent to the distance kind of thing. We integrate the distances between them. Energy is kind of the energies, difference between the energies. L2 is kind of difference between the displacements. So these are the measures of error. So when we do FEM, we calculate one of these errors to see how much is the error, and we have some tolerances where we want to design our model within those tolerance limits, and we check if the errors are within those limits, and if the errors are acceptable for us, then we proceed with the design. Let's say if error is high and we and it is not within our tolerance, then what we have to do is we need to do the convergence study. For any numerical analysis, we can, as you discretize it more and more, you will reach to the exact solution better. That is, like, we call it convergence. So in FEM, there are two types of convergence. Like, as you increase the number of elements, the error reduces, or as you increase the order of polynomial used for approximation, even then error reduces. So whenever the error is high and it's not acceptable for a design, you can just need to do one of these things. For convergence, generally we say that the norm, energy norm UH minus UM is less than CH power P. C is some arbitrary constant. H is the element size, and P is the rate of convergence. So, for reducing error, reduce the element size which indirectly means increase the number of elements. This is called H convergence. Or else you can do the second thing, which is increase the order of polynomial used for approximation. It is called FEA convergence. So you, until and unless the error is acceptable for the design, you can go on increase the number of elements, or you can go on increasing the order of the polynomial until it suits better. So just a quick recap, we just saw the sources of error, we saw the what measures can be used for error, and then what is convergence and ways to reach the solution with acceptable tolerance. In today's for today's tutorial, I would like to we will solve a problem, and then we find the error different types of error estimations in this problem. We will look at how to find errors for the problem which we solved in the previous tutorial. I'll just recap the question for your understanding. It was a simple bar problem with a varying cross-sectional area. It is a vertical bar. It's starting from height and length is 2 meters, and a distributed load of 20 kilometer per meter is acting on top of the bar, and bottom it is fixed, and area on the top width is 0.5 meters, and on the top breadth is 0.5 meters, and at the bottom it's 1.5 meters. This was the problem which we were solving in the last class. Today we will try to find out the different types of error for this problem using FEM solution. As this is the bar, the governing equation for this problem is minus d by dx e a of x du by dx is equals to f, where boundary conditions are given as at x is equals to 0. One more thing, we have simplified the problem into 1D bar problem, where at the top force is given as 5 kilonewton. For detailed explanation, please refer to the previous video. At x is equals to 0, force is 5 kilonewton, and at x is equals to 2, displacement is 0 as it is fixed. This is the problem. First we will find out what is the analytical solution, because in order to find the error you need to know the exact solution. Let us find out the analytical solution for this problem, then we will look at what we found in the FEM solution. So analytically, how you will solve analytical solution. So for analytically solving it, you need to use minus d by d e a of x du by dx is equal to f. F in our case is 0 as there is no body force, and A of x, in the last class we found that it is 1 by 4 times 1 plus x. So if you integrate it, you will get it as E A of x du by dx is equals to integrating on both sides gives A du by dx is equals to some constant c. And if you remember, we have a boundary condition at x is equals to 0, p is equals to 5 kilonewton. That is, p is nothing but EA du by dx at x is equals to 0 is equals to 5 kilonewton is equals to c, implies c is 5. And then at an A is nothing but 1 by 4 times 1 by 1 plus x du by dx is equals to 5. So du by dx is equals to 5 times 4 is 20. And if you remember, we took E as 1 just for the case of simplicity. 20 by 1 plus x. So if you integrate with respect to x, you will get a solution of u, which is nothing but integral of 1 over 1 plus x is log of 1 plus x, and obviously an integration constant. So you can use the another boundary condition at x is equals to 2, u is equals to 0, implies if you substitute this condition in this equation, you will get 0 is equals to 20 log 1 plus 2 plus d. So you will get d as minus 20 log 3. So final solution of u is equals to 20 log of 1 plus x minus log 3. One place here it should be 4 should be minus sorry, this thing should be natural log, not this log. And for the FEM solution, we will use the solution from the previous tutorial which we solved. Before doing there, I just realized that I did some silly calculation mistakes during that time. I have modified that and I will update the updated file in the drive folder. You can just see them. Just some small calculations I made mistakes. So this was our final FEM solution which we found out. This was for 2 elements and linear interpolation functions. So
and the FEM solution is denoted by UH. So we have FEM solution, we have analytical solution. Let us see how to calculate different types of errors. The first type of error is pointwise error. This one is a function which is it is a function, so error is it shows the error how it varies with h, and it is just the difference between the analytical solution and the FEM solution. So pointwise error. It is just the analytical solution minus FEM solution. So in this case we will have 2, that is from 0 to 1 and from 1 to 2. And this is the analytical solution. We just move this a bit. And then minus 64 by 3 plus 40 h by 3. This is from the previous tutorial session. And then similarly for values between 1 and 2, analytical solution is expression is same, but the FEM expression changes a bit. So this is the pointwise error, and it is a function of s. Let us just see the error value at some few points. Let us just see at the nodes, which is at x is equal to 0. Error is 20 minus log 1 is 0 plus natural log 3 minus 64 by 3, which is nothing but 20 log 3 minus 64 by 3. You quickly calculate it using your mobile. It comes out to be 0.64. This is the error at point x is equal to 0. Let's say at x is equal to 1, it is nothing but EP 20 times minus natural log 2 plus natural log 3 minus 64 by 3 plus, sorry, this is 40h plus 40 by 3. I will just once again calculate it using mobile and write the value here. 20 times minus natural log 2 plus natural log 3 minus 64 divided by 3 plus 40 divided by 3. It comes up to be 0.11. and for x is equals to 2, the first analytical expression is 20 times minus natural log 3 plus log 3 minus 8 times 2 minus 2. This is 0 and this is 0. The error is 0. Just notice that at x is equals to 2, it's the fixed boundary condition, and we have applied that boundary condition. Wherever we apply the Dirichlet boundary condition, that is left displacement boundary condition, we get the exact solution at those points. That's why the error is 0 at x is equals to 2. So this is how the error varies with x. Like as you come closer to boundary condition, it is decreasing. This is the pointwise error. Let us go to next type of error. Next error, it's maths norm error. It is also just the difference between analytical solution and exact solution and the FEM solution, but instead of writing the whole expression, we are saying is just the maximum value of the expression. So this is the maths normal error. So it will be the maths of this expression will be same as the previous one. So I'll just take this. So it is the maths of this expression, maths of mod of this expression. Please notice that you observe that it is decreasing function from 0.64 to 0. So the max norm of this is nothing but max norm error of this problem is 0.6. Let's go to the third type of error. It is the energy norm error. I'll just copy this expression. This is the energy norm error. As I said, 2m is the derivative of the order of derivative of the problem. In our case, order of derivative is 2, so m is equals to 1. So we need to find the first order derivatives in this case, which will be, and the limits are from 0 to 2. Our domain is from 0 to 2, and m is 1, and it will be du by dx minus duh by dx whole square dx power 1 by 2. So for this bar problem, this is the energy norm. Let us calculate the du by dx and duh by dx. Analytical solution is given here. Let me just take it. So u is this one. So du by dx will be the derivative, which is nothing but minus 20. Natural log derivative is 1 by x, and remaining is the constant. So this is the analytical du by dx, and then let us take the FEM and then calculate its derivative. This is the FEM solution. Implies duh by dx is equals to minus 40 by 3 and minus 8. Both are from 0 to 1 and 1 to 2. So we have the derivatives for both analytical and FEM. Let us substitute it back into the energy norm and then find its value. So it is nothing but integral we have two expressions, so we have to separate the integral from 0 to 1 and 1 to 2. First, for 0 to 1, the expression is analytical solution minus FEM solution whole square dx plus from 1 to 2 analytical solution minus FEM solution square dx, and everything raised to the power 1 by 2. Let's slightly simplify this. 0 to 1 mod minus 60 plus 40, it's minus 20, 40x, you can just take 20 common, minus 3 plus 2 minus 1 plus 2x divided by 3 times 1 plus x whole mod whole square dx plus 1 to 2 divided by 1 plus x. 8 minus 20 is minus 12 plus 8x whole square dx power 1 by 2. This is kind of a complex expression to solve it manually. Instead of solving manually, we can directly use online integral calculator. There is one thing called a Wolfram Alpha which is available freely. Let us use that and see how to calculate. This is the Wolfram Alpha page where you can calculate some integrals directly. Let us use this and find out the integrals. You can see the symbols here and you can see that it's the definite integral. Let us see the first integral 0 to 1 and the integral is over dx, and then we have a numerator 20 by 3 20 times minus 1 plus 2x, and in the denominator we have 1 plus x, and everything is squared. So if you enter the expression and then make it equals to, it will directly calculate and see the value. So it shows that the error is 8.093 0993. Okay, and let us see the second expression. This is just the first expression. Second one is on the numerator, it's 8x minus 12, and in the denominator it's 1 plus x. So this is the second expression and it shows the integral to be 42.193. So we got first expression value as 8.099 and the second integral as 42.19, and we have a square root over this, which is nothing but roughly 50.3 square root. Let me just calculate the value and write it here. Square root of 50.3 is roughly 7.09, and this is the energy norm. You can notice that when compared to pointwise error and maths norm error, energy norm is higher in value. Let's go to the final norm calculation, which is the L2 norm. In the L2 norm, it's an integral, but instead of derivatives, we directly take the primary variable and then find the integral. So this is the L2 norm. So as usual, we have two expressions, so we need to divide the integral into 0 to 1 and 1 to 2, and the analytical expression is this is the analytical expression. Copy it. Analytical expression minus FEM solution is 64 by 3 plus 40 x by 3. This is between 0 and 1 dx, and from 1 to 2 analytical expression doesn't change, it's the same, but the FEM solution is 8 times 2 minus x, and whole to the power of 1 by 2. So this is pretty complex integral. It's difficult to do it manually. You can just once again use Wolfram alpha to calculate it. Let us calculate the L2 error. This is the first expression of the L2 error, and it is given as the value of this is 0.037, and the second expression, this is the second part of the expression of L2 error, and it is 0.06. It's 0.06. So the first expression is 0.307, and the second expression is 0.029063, and it's under root, and the value is, let's use 1.307 plus 0.063, it's 0.37 under root. Is 0.608. This is your L2 error. I'll just revise whatever we were doing till now. So we want to calculate different types of error, and we took the one example problem and we solved it analytically. It's a bar problem with variant area, and the solution displacement solution is found out. It is in logarithmic. It's not at all linear, but we are comparing it with the FEM solution, which we took linear shape functions, and this is the FEM solution which we achieved. And for this we have calculated the pointwise error, which gives error at all the points. Then the maximum norm error, which is we got it as 0.64. Then the energy norm error, which we got it as 7.09. We notice that energy error is larger when compared to other types of error. And then L2 norm error. L2 norm error is 0.608. So in this way we can calculate the errors when we used FEM. So while designing, when generally we usually have some tolerances, so we even have tolerances for our problems. Let's say if the error is within the tolerance regions, we are happy with the uh, numerical solution, and then we just accept the design. But if our tolerance is if the error is higher than the tolerance, then we cannot accept the solution. We need to do the convergence study. So we need to make the solution to converge. In order to do that, we have two ways to do it. Either reduce the element size or increase the order of the polynomial. So here let us see both the effects and see if the error is reduced or increased. First we will see the effect of element size. We already whatever we solved till now, it is for the 2 elements using FEM. If we use 3 or 4 elements, it should error should decrease. But as we are doing it manually, just for the sake of saving time, let us do it for one element and see if the error has increased. Then it's like we'll see for one element how much is the error, and for 2 elements how much is the error. So let us quickly solve the problem for one element. So for one element, u1 and u2, this is the boundary condition. I will just directly take the weak form from the previous tutorial so that we can save time. This is the expression. Sorry, not this. This even shape functions change in our case as it is. Okay, no, we can definitely use this. I will copy these two equations. So these are the linear shape functions. If you want to like to know how we ended up with this expression, just refer to the previous tutorial. So in this case, the element is from 0 to 2, so L is 2. L is equals to 2 here. Let's quickly calculate the expressions for all the expressions. K11 is 0 to 2 E 1 by 4 1 plus x times 1 by x square is 1 by 4 dx. We assume E is equals to 1 just for simplicity purposes. So it's 1 by 16 times x plus x square by 2 with the limits from 0 to 2. It's 1 by 16 times 2 plus 4 by 2. It's 1 by 4. K11 is 1 by 4. We observed that K2, K1 to 2, 1 to 2, everything will be same, just the symbols will be such that 1 minus 1 minus 1 1. So if we write the expression, it will be 1 by 4 times 1 minus 1 minus 1 1, and u1 u2 is equals to f1 and f2. Here u2 is fixed boundary condition, so is equals to 0, and f1 is nothing but p is equals to 5. So using these two we can solve. u1 is equal u u1 by 4 is equals to 5 and plus u1 is equals to 20, and from this u2, which is already a boundary condition, is 0. So for one element u1 is 20 at x is equals to 0 and u2 is equals to 0 at x is equals to 2. So u is a linear ax plus b. Is equals to 20 at x is equals to 0 implies b is 20, and u is equals to 0 at x is equals to 2 implies 2a plus b is equals to 0, which is nothing but a is equals to minus 10. The expression from the finite element is minus 10x plus 20. This is UH, but in this we are using only one element. Let us calculate error using this for this one element. But instead of all the errors, let us just take one error and find its values to see how much we are getting. Let's take the maximum. Let's take the maximum norm error, which is the max of the difference. And analytical solution wouldn't change. maths of minus plus 10x minus 20. To find the maximum of this expression, we need to take the derivative and make it to 0, then we can find the maximum for this expression. Minus 20 by 1 plus x plus 10 is equals to 0. 1 plus x is equals to 2. X is equals to 1. So we have the maximum value of error at x is equals to 1. We will substitute it and then see the value. So 20 times minus natural log 2 plus natural log 3 plus 10 minus 20. We will just calculate it on phone and write the value. 20 times minus natural log 2 plus natural log 3 plus 10 minus 20. It is coming out to be, and there is not a mod 1.89. This is the maths norm error for one element. And if we see the maximum norm error for two elements, it is 0.64. For two elements, maths norm error is 0.64. You can clearly see that the error reduced from by increasing the number of elements or reducing the size of the element. Similarly, if you go for 3 and 4 elements, error will further reduce as the size of the element reduces. This is nothing but the H convergence, which depends on the size of the element or the number of elements. Then we will look at the P convergence, which depends on the order of shape functions which we take. P convergence. Order of polynomial. Till now we were solving using first order shape functions, that is linear functions. Let us do with the second order shape functions and see what happens. Second order approximation. I will take the weight form from the previous session. Weight form doesn't change until we substitute the shape functions. So I can use this expression. So this is the weight form expression which I have, and second order approximation will be for we'll use standard shape functions which in local coordinate system from -1 to 1. If this coordinate system is zeta, first shape function will be zeta into zeta minus 1 by 2. So at zeta is equals to -1, it will be 1, and at zeta is equals to 0, it will be 0, and at from zeta 1, it will be 1. So this is the first shape function. And second shape function will be zeta minus 1 into zeta plus 1 by 2. That is at minus 1 and at plus 1 it will be 0, and at 0 it will be 1. When zeta is 0, it should be 1, so it is minus. So when you substitute 1, it will be, when you substitute 0, it will be 1. And for n3, it is zeta into zeta plus 1 by 2. Which will be something like this. There won't be any 2 here because when we substitute 0, it will be 1. It's nothing but you can write it as 1 plus zeta into 1 minus zeta. So these are the 3 shape functions for the second order approximation. So u will be n1 u1 plus n2 u2 plus n3 u3. Let us just take just one element, just for the sake of solving it easily. We can compare it with one element first order approximation. So as our shape functions are in xy coordinate system, we will convert area as well. Our actual problem is in 0 to 2, but this local coordinate system is in from -1 to 1. This is x and this is zeta. And a of x is 1 by 4 times 1 plus x. We want to find a as function of zeta. At x is equal to 0, zeta is -1, and at x is equal to 2, zeta is 1. It's just that x is equal to zeta plus 1. It's very obvious. This is the relation. So if you substitute this expression in this area, you will get a as a function of zeta will be 1 by 4 times 2 plus zeta. So now you can substitute the expression of area as well as du by dx and dw by dx. Okay, you need dx, which is nothing but d zeta. Both are same here. You need an expression for du by dx. Du by dx will be du by d psi times d psi by dx, which is 1 here. Du by d psi, this one will be 1, and d and 1 by d psi u1 plus d and 2 by d psi calculate the derivatives of the shape functions. dn1 by d theta, its derivative half xi times xi minus 1, which will be half of 2 xi minus 1. And for the second shape function, it's 1 minus xi into 1 plus xi. It is 1 minus xi square, which is minus 2 xi. And the third shape function derivative, it's half times xi into xi plus 1, which is half 2 xi plus 1. These are the derivatives of shape functions, and we need to substitute this in the weak form which we generated. And for the w we take n1, n2, n3, so we will get 3 equations. For first case, when w is equal to n1, the first equation would be in the form e of x is 1 by 4 times 2 plus psi, and du by dx is dn1 by d psi u1 plus dn2 by d psi u2 plus dn3 by d psi u3. And obviously there will be d psi by dx, but it is 1 in this case. And then there is dw by d psi, which is dn1 by d psi times d psi, and the limits are from -1 to 1. So if you substitute these terms, we assume d is equals to 1, so 1 by 4 integral -1 to 1 2 plus psi dou n1 by dou psi is half into 2 psi minus 1 times half into 2 psi minus 1 d psi u1. u1 is a constant, that is the value of degree of freedom at first node, so it can be out of the integral. Similarly, for if we separate for other two terms, it would show up as this way: minus 2 psi into half times 2 psi minus 1 d psi u2, and third term will be dn3 by dx, which is half 2 psi plus 1 into half 2 psi minus 1 dx u3. So this would be k11, this would be k12, and this is k13. So this is the first equation when double weight function is n1. For weight function is equal to n2, the expression will be similar, just w changes. So I'll just take this and edit it. everything will be same, just here w will be n2, so this will be in this manner. So if we separate the terms and write it, and d is 1 by 4 2 plus psi times dn1 by t psi is 2 half 2 psi minus 1 into minus 2 psi d psi u1. This is first term. Second term would be 1 by 4 2 plus psi minus 2 psi times minus 2 psi d psi u2 plus third term is 1 by 4 2 plus psi dn3 by d psi is half 2 psi plus 1 into minus 2 psi d psi u3. So this first term would be k21, second term would be k22, and third term would be k23. This is the second expression, and finally we will have third expression w is equals to n3. It will be same. Yes, this final term would be 3, and if we find out the terms of the case, it would be 2 plus psi half 2 psi minus 1 times dn3 by 2 psi plus 1 d psi u1 plus 1 by 4 minus 1 to 1 2 plus psi into minus 2 psi times half 2 psi plus 1 d psi u2, and third term will be minus 1 to 1 2 plus psi dn3 by dn psi is 2 psi plus 1 times half psi plus 1. This will be k31, this will be k32, this will be k3. I'm not finding out the force terms, but they will be present, and I will substitute the forces on the right hand side. First, we will find out the individual A and we'll see what they will be. The expression for K11 will be 1 by 16 minus 1 2 plus psi times 4 psi square minus 1, and then it will be 8 psi square minus 2 plus 4 psi cube minus psi. Yes, 4 psi cube plus 8 psi square minus 8 minus Sorry, small mistakes in integration. These are not 0. Even the terms will be 0. So it would be 12 by 3 into 2 plus 2 times 2. For it's 3 by 4. Similarly, I need to change previous integrals as well. Even terms are 0. 5 by 3 times 2. It's 5 by 6. Two by 3 times 2. 4 by 3. 8 by 3 into 2 minus 2 into 2. 4 by 16. 4 minus 3. 1 by 4. This is 0. Sorry about this. Now we can form the stiffness matrix. G11 is 5 by 12. 1 2 is 1 by 2. 1 by 4. 5 by 12. 1 by 2. 1 by 4. It is same 1 by 2. K22 is 4 by 3. K23 is 5 by 6. 3132 will be same as 13 and 23, and 33 is 3 by 4, and we have our u1, u2, u3 is equals to f1, f2, f3. This is the u is equal to f format. Now we need to apply the boundary conditions. In this case, u3 is 0 as it is fixed, and f1 is p, which is 5. f2 will be 0 as it's an internal node, and forces its cancelled out. So for solving, 5 by 12 u1 plus half u2 is equals to 5, and 1 by 2 u1 plus 4 by 3 u2 is 0. u1 plus 6 u2 is equal to 12 by 60. 3 u1 plus 4 to 8 u2 0. 5 times minus 8 by 3 u2 plus 6 u2 is 60. Minus 40 plus 6 3 is 18. There is a minus here. And also minus here. It's coming as 8.18. So u1 is 8 by 3 times u2 21.82 and u3 is 0. So these are the FEM solutions. So expression for u can be n1 u1 plus n2 u2 plus n3 u3, or else you can just take the second order ax square bx plus c. U at x is equals to 2 is 0. 4a plus 2b plus c is 0. U at x is equals to 1 is